I like to hear something that sounds impossible and then try to be creative and find a way to go around the hurdles and make it possible.
String theory, loop quantum gravity. Do you have a preference between those two?
I see a third way. I think you have to change both in order to bring them together. I'm taking some steps towards that. It's like completely mine, an approach of myself.
It's often said that fundamental physics has been stuck for decades because the experiments required to probe quantum gravity need galaxy-sized accelerators and billions of dollars, etc. You've heard this before. Professor Ivette Fuentes works in relativistic quantum information, combining quantum field theory with curved spacetime to answer questions we weren't able to answer before. She's repeatedly predicted effects that were later verified in labs, such as how the quantum vacuum induces geometric phases, how to use the dynamical Casimir effect to implement quantum gates, and how superconducting circuits can be used to study physics at the intersection of quantum physics and relativity. I'm Curt Jaimungal, and on this channel, I interview researchers about their theories of reality with rigor and technical depth. I'm so excited to speak with Ivette Fuentes. This is the second time. The first time I spoke with her, it went viral, and that will be listed in the description. Professor Fuentes also hinted in this episode that she's developing what's called a third way to quantum gravity, modifying both quantum mechanics and general relativity instead of forcing one to dominate the other. After years of wrestling with this new model, it turned out surprisingly simple, making her wonder how she missed something that was staring her in the face all along. Ivette, it's great to have you back on. Thank you for coming.
No, on the contrary, thank you so much for having me back.
Your city is lovely. I'm here in Oxford. It's cold. We're wearing coats, as you can see.
Yes, well, I actually live in London, but I visit Oxford once in a while. I have a PhD student here. So Melanie, who's over there. So I come and I'm in a fellow in Keble College here in Oxford, but my main position is at the University of Southampton. But I come once in a while here to Oxford, and I agree that it's lovely. Actually, my son is studying here.
What is he studying?
Philosophy of philosophy. He just got started. I was going to say philosophy of physics, but that's his first essay is going to be on philosophy of physics. Yes, which I thought it was nice.
Okay, so bring us up to speed. The viewers who are watching this now most likely have watched our first podcast together. For those who haven't, can you tell them what our first podcast was about and then where your mind is now?
Yes. Well, I think the first podcast was covering many different topics, covering sort of a little like the evolution of my career maybe, or my thoughts in the interface of quantum mechanics and general relativity. I think I was making a big point on how we need experiments to guide us. So I'm a theoretician, but I love experiments, and my background is in quantum optics. So that's a really privileged field that has, like this interaction between theoreticians and experimentalists on everyday basis. People can work together. And I think that's why the field of like quantum technologies and quantum optics has made so much progress, because you really have, both the theory and the experiment working together. So I've been kind of trying to bring this to the interface of quantum mechanics and general relativity.
So you're a theorist and an experimentalist, or just a theorist?
No, I'm just a theorist that likes to propose experiments. I like to talk to experimentalists. I also like to talk to philosophers, by the way. But no, I'm like a theoretician.
Does that make you a phenomenologist, or is that different?
Oh, no, I guess that's different, because I do like, theory. Well, now I'm building like a new theory, or more, I would call it more of a model of my own. But before, I used quantum field theory in curved spacetime and quantum metrology and quantum information to study, things in the interface. So these are established theories, but then I would put them together in a special way, let's say in a different way, to answer questions that people were not able to answer before, or new questions that came up, and so on. But these were like established theories that we kind of just used in a different way. But that's not sort of phenomenology, no? So, and then I come up with maybe a new detector model, or a new effect that I thought it would be nice to test if this is real. And then I would work towards proposing an experiment which could be tested either, with current technologies or in the near or mid future. So I think because of my background in quantum optics, I always put like this emphasis on I want to do physics, theoretical physics that can be tested in the experiments. And I always put like this bar on me, like, sometimes a bit too strict, I think.
What do you mean?
But, well, that sometimes maybe I would find something interesting. And if I found that it was a bit too far to be tested in the experiment, I would just kind of just say, okay, this is not observable. Let's try to find something else. And I think much later I found that, oh, look, I mean, these ideas are even further away to be tested in the experiment, yet people published, So I noticed that I was putting a lot of sort of the bar really high for the things I propose to be tested.
I see. So too much pressure on yourself for the experiments to be near term.
Yeah. Yes. Yeah, I have, which I think it's a good thing. I think that made my physics in a way sort of better. And this pressure that I self-imposed, I think at the end of the day has given like good results. And I have had some experiments already being, verified. Some, let's say not experiments, but I've had some of my results tested in the experiment and actually sort of positively, verified in the experiment, which gives you as a theoretician, like that's kind of what you really want, no? As a theoretician, your peak like this of what you want is that somebody tests what you do in the lab and finds that you were right. So I have a nice example of maybe that was, should I tell you about it?
Please.
So when I was a PhD student, I did my PhD at Imperial College with Peter Knight, who works in quantum optics. And I became interested in Berry's phase, from Michael Berry. So how he talks about, well, the typical example is that you have a spin 1/2 particle in a magnetic field. And then if you change the magnetic field in a cyclic way, then you say, okay, let's say you have the spin 1/2 particle in the up direction, and then you change very slowly, adiabatically, the magnetic field. The quantum state will follow, and then you make, let's say, a trajectory like a circle, and then you come back where you're still in the same state. But Michael Berry showed that the state can pick up a phase, because states in quantum mechanics are indistinguishable up to a phase, and this is called the geometric phase or the Berry phase. So when I was a PhD student, this was kind of, although Michael had sort of done the physics of these phases and so on earlier on, they kind of were going through a revival because of some ideas that, because they're sort of resonant to noises, at the end, what really matters is sort of the area enclosed by the state, and not like maybe little changes in the laser or fluctuations like this. They get sort of averaged out. So they seem to be resonant, and people thought, oh, maybe we can use them for quantum computing. So that was kind of the motivation. And so as a PhD student, I got interested in that. And I started to, let's say, propose experiments on how to measure certain effects. But one thing that I found was this example of the Berry phase was usually discussed with classical fields. So you have the spin particle is a quantum system, but the electromagnetic field driving it is a classical field. So then I thought, oh, wouldn't it be nice to put a quantum field instead of a classical field and see what happens with these Berry phases. So I studied that, and in particular, a big difference that you have with a quantum field as compared to a classical field is that the quantum field has this sort of vacuum energy. So if the field was classical and you say you have no field, well, the system would not get a geometric phase, would not do anything. But what I saw is how the vacuum state of the field could be driving the states to get geometric phases. So this was called vacuum-induced geometric phase. So I wrote that on my PhD. I was kind of very pleased with it. Michael Berry was my examiner, so that was also very nice.
Cool.
He was tough and strict, but it went very well. So it was really nice to meet him. And then after that, somebody wrote a paper saying that effect did not exist. And there was a back and forth, not with me, because I had moved on into relativistic quantum information. And people were saying, like, Ivette, you need to go back and defend your work because these authors, wrote that this effect does not exist. But I felt I was just so invested in the new work I was doing. And I thought, no. I mean, I did my contribution there, and I'm not gonna go back. But it gave me quite a few citations because there was a community fighting over it. And then finally, in ATH, the group of Andrea Warloff, he measured it. And it was very funny. I went there to a conference on time. I wasn't expecting at all, to hear about this. I was at the conference, and somebody came and said, "Oh, are you Ivette Fuentes?" And I was like, "Yes." "Oh, I need to talk to you." I was like, "Oh, that's very funny." And he said, "Oh, I'm a postdoc working on vacuum-induced Berry phase." I was like, "Oh, that's very nice." He said, "We very recently verified your results, and the effect is there, and we will very soon publish it." And I was like, "Oh, wow." That was super exciting.
Congrats.
Yeah, so that's a nice example of some predictions and that then get tested is very, very satisfying as a theoretician.
Tell me another example of some things you've predicted that have gotten tested.
Okay. So, I started to work in the interface of quantum mechanics and relativity using quantum field theory in curved space-time. So that's what is now known as relativistic quantum information. And one of the things that we noticed was that you can implement quantum gates by sort of relativistic motion. So we were looking at things like the dynamical Casimir effect. So that is, you have two mirrors and a quantum field. And then if you move the boundary conditions, you excite particles out of the quantum vacuum. So it's called the dynamical Casimir effect. Then, like more recently, can talk about that later, but we sort of were able to describe this situation in curved space, which was something that was not possible before. And I was very keen in doing that also because of a number of applications that you can find to that. But back in the day when I started to work on relativistic quantum information, we noticed that by moving sort of the cavity in a certain way, you would be able to implement quantum gates, in particular a cluster state. So a cluster state is known as a universal resource for quantum computing. So they're states that are like highly entangled, and you can use them to do quantum computing with them. And we wrote a paper, a theoretical paper showing how you could implement a cluster state changing sort of the cavity in space or something like this. But you can just do it by modulating the boundary conditions. So then Chris Wilson in the University of Waterloo became interested in our work. And he had superconducting circuits. So you have also like, let's say like a cavity, and then you have boundary conditions. Like instead of mirrors, the boundary conditions are fields.
Okay.
And then you can change sort of the conditions of the boundary conditions and move them by changing fields that go through a squid. This is maybe
a squid.
Squid is just some sort of maybe I shouldn't go into so much.
What does it stand for?
But superconducting.
I see. Okay,
I'm not remembering right now.
Yeah, whatever. We'll place a link on screen.
Yeah, just but the point is that you change a current that goes through this electronic device, and what it does is that it produces these fields that you can modulate. So Chris Wilson did with Pearl Delsing in the University of Chalmers a really beautiful experiment in which, by doing that, they demonstrated the dynamical Casimir effect. So this was like a big thing because the effect is very small. So if you think about mirrors that move, let's say, close to the speed of light or something like this, but real mirrors, right? You would produce something like 2 photons in the lifetime of the sun or something like this. So it's like a super small effect from quantum field theory. And obviously, because of these numbers, people were not very hopeful that the dynamical Casimir effect could be demonstrated in the experiment. However, the group of Pearl Delsing had this wonderful idea of using the superconducting circuits, because in that case, instead of mirrors, using fields as a boundary condition, you can modulate them very fast to 1/3 of the speed of light. And, these starts to be the scales that you can show that you are exciting particles out of the quantum vacuum. And so they wrote a really beautiful paper showing this. Gosh, I forgot the year, but this was already maybe 2011 comes to my mind, but it might have been earlier than that.
Sure, we'll place it on screen.
Yes. So then this was exactly sort of the sort of situation that we were considering, only that it was going beyond just showing that you create particles, but that you would be able to create this resource for quantum computing, cluster states, or other quantum gates. And then Chris took the simplest case for a quantum gate in this system and showed in his lab. Chris Wilson was working with Pearl Delsing in Chambers, but then at the time he finished his work there and moved on a permanent position to the University of Waterloo, where he set up his lab, and he did this experiment and verified our predictions. And that I'm in the paper with them. So that was also kind of very exciting for me.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount. One of the reasons I was so excited to speak with you the first time was because sometimes people say that there's a stagnation in physics. Okay, is there? Well, what do they mean specifically? It's usually with regard to fundamental physics and the lack of some new law that's been experimentally confirmed. There's two sides to this. There's theorists and then there's experimenters or experimentalists. Okay, you sit in an interesting in-between boundary. But anyhow, I've always wondered if it's because are we not being ingenious enough with our experiments? And in my mind, I was sometimes blaming experimentalists. Just theorists would say, no, you shouldn't blame the experimentalists.
Yes.
Okay. But anyhow, why I got excited about your work was there's so many effects that are so tiny, you would think it would be some advanced civilization some 100 years from now that would be able to discern them.
Yeah.
But you just described something about Casimir mirrors,
Yeah.
which you would think you would need to accelerate them to the speed of light, but no, we can do something without mirrors per se,
Yes.
but with quantum fields that
Yes.
mimic the same effects, and you can test something about
Yes.
what they would be like if they were Casimir mirrors. You also showed that quantum gravity tests are not that far off. In fact, you came up in our previous podcast, which I'll place on screen, with some tabletop experiments.
Yes. Yeah, I mean that's kind of the fun of it, right? I think that I find that's what I like to do. I like to hear of something that sounds impossible and then try to be creative and find a way to go around the hurdles and make it possible, no? So, by the way, the experiment that we were talking about by Pearl Delsing was controversial at the moment because there were not mirrors and there were like these fields. People were saying, well, it's not really the dynamical Casimir effect because the dynamical Casimir effect is about mirrors. But when you're like a theoretician, at least like how I was working, the theory was like you have a boundary condition. So the physical realization of the boundary condition for me as a theorist is not that important as long as it is a boundary condition that is doing and creating the effect. But I was really surprised on how controversial that experiment was and how there was like discussions and some people even sort of getting angry about it. But well, from my perspective, having a mirror or a field doing the job is as good.
Okay, I want to get to the controversy about the dynamical Casimir effect.
Yes.
Or experiment. Can you first outline what the regular non-dynamical version of the Casimir effect is for people who don't know?
Yes.
And then get to what the dynamical version is, just a quick recap, and then what the controversy is.
Yes. Okay. So the Casimir effect is you have two mirrors and you have a field inside. And then if the field is in the vacuum state, well, if the field was classical, you would have like no field, let's say, and the mirrors would just sit there and there would be sort of no effect. But what Casimir predicted and then was tested in the experiment, that's not that difficult as the dynamical case, was that the fact that you have a quantum field and that the field can be in the vacuum state, that creates a force between the mirrors.
Over and above just their gravitational force.
No, it's not. It's a force due to the vacuum state of the electromagnetic field.
Oh, what I mean to say is this is not due to the electrical... Sorry, this is not due to gravity.
No.
Because gravity you would expect, even classically, for them to slightly move together.
Yes, I mean, it's a super small... for the sort of systems, it's negligible. The gravitational effect for the mass of the mirrors is very, very small. But no, yes, it's not a gravitational effect. It's a effect of the electromagnetic being a quantum field. So in a way, it's a physical verification that the electromagnetic quantum field is quantum and that the vacuum state it has effects. There's a connection with what we were talking about, the Very phase, right? Because I was talking about how the vacuum of the quantum field was inducing Very phases. That's one example. And this is like a different example where you're saying due to the vacuum state of the quantum field, there is like this attraction between the mirrors. And that's a dynamic, but that was like tested. I don't remember when, but
decades ago.
Before, yes. And then there was the dynamical version of that, and the dynamical version, I find it beautiful. I think the easiest way to understand it is that now you have again your two mirrors, and you have your quantum field, and let's say your quantum field is in the vacuum. But now as you suddenly move the mirrors, then the vacuum is a different one. So the vacuum here is different from the vacuum there. But if you're moving the mirrors, what you're doing, let's say that you're in the vacuum here, but now you move them, the vacuum is different. So what that makes is that you excite particles. So you say, where does the particles come from? If you're kind of, if you're in if there was no particles before. But it's because the vacua are not equivalent. And of course, you're pumping energy into the system by changing the mirrors. But it is like a signature of quantum fields. So it's an effect that is, clearly a quantum effect. And I think it's a beautiful, it's a beautiful effect.
In just a moment, in this gesticulation, you keep turning your hand, so not just moving them like this, but you curve your hand. Is it important that the mirrors themselves curve in the boundary condition?
No, that's like my old dancing.
Okay.
No, they should be. There is so
it's just the distance that's changing between them.
Yes, no, they should be like completely parallel.
I see.
But I find that difficult to do with my hands. And then the only thing that changes is the distance between them.
Got it.
Yeah.
And particles are produced. Photons are produced, or other particles?
Well, I mean, photons are produced, but later on I studied the effect with phonons on a BC, on a Bose-Einstein condensate. So it's like an analog, but it's another instance of the effect, but with, let's say, particles that propagate at the speed of sound instead of the speed of light. But, well, maybe we can talk about that later.
Now, you mentioned the electromagnetic field that's quantum, but what about the other fields like the gluon field or quark field or what have you? Are there other fields that have a contribution to the Casimir effect?
Well, they would in principle all be there, right? Because when you have the vacuum, it's the vacuum of everything. But what happens with, let's say if you were to excite particles from, I don't know, some other field, you would need a lot more energy to see the particles. I'm guessing just now, why wouldn't you see that? But that's like what I think should be happening is that if you calculate it, what happens with, I don't know, a neutrino field or something like this, that it would be even more difficult to see. But I don't work in particle physics, and I don't work with neutrinos or anything like that. So I'm just guessing.
Well, it sounds like you work in particle physics.
Well, it depends what is understood by particle physics. I mean, the only particles I work with are the electromagnetic field and the like phonons. Yeah.
Do you consider yourself a relativist?
I consider more of myself a quantum physicist with a love for relativity. It's interesting because it's really hard to have a really strong understanding of both, because both fields are, it takes you like a lifetime to really understand them deeply. So most people would go and work on quantum mechanics or quantum information, quantum optics, and with the time acquire like a really deep understanding of that. And then other people would go and do the same with gravity or quantum field theory and Curt spacetime or something like this. And doing both is not so easy. And although I've been working with, I've been trying to work with both for now. When did I start this? In 2004, 2005, something like that? Well, really after finishing my PhD, I still feel like quantum mechanics is my strongest arm, let's say. Mm-hmm.
Okay, so we're going to get Roger Penrose here. Roger Penrose is downstairs. And in case you're wondering, I just spoke with Roger, and that is on the channel or is coming up, so feel free to subscribe. There's going to be a joint conversation between Roger and Ivette, as Ivette is proposing experiments that test Roger's collapse model. We'll talk about that with Roger. But a question I have for you is, as a quantum theorist who's extremely strong relativistically or general relativistically or what have you, there's usually two routes to quantizing gravity. Now, of course, we can go to, well, we shouldn't be quantizing gravity. We should be adding gravity to quantum or gravitizing the quantum or what have you.
Yes.
Whatever slogan one wants to use.
Yes.
But let's talk about quantum gravity. It's usually said that if you're a quantum field theorist and you go into quantum gravity, you become a string theorist. If you're a relativist and you go into quantum gravity, you become a loop quantum gravitivist.
Yes.
Okay. You are strong in both.
Yeah.
Do you have a preference between those two? Do you also see it similarly? Or do you see a third way? Or what's going on in your mind?
I see a third way. Yeah, definitely.
Okay.
Coming up. Well, okay.
Give me a teaser. Give me a teaser.
No, I think that I've come up with a different way of approaching the questions, but they're still like a baby steps, or, well, I wouldn't say baby step, but it's not the full thing yet. But it is kind of a different way of doing things that I've been working with that have ingredients of both quantizing gravity and gravitizing quantum theory.
Okay, I shouldn't have said give me a teaser because now I'm too teased. So that was like a moosh boosh. Is that the correct term? It's the small little tidbit. Give me a starter. Give me an appetizer then.
Yeah, I already felt like, oh, maybe I already said more than what I wanted to say. I guess things started because, well, maybe this is something that we can talk with Roger, but Roger has been pointing out for a long time now that we should gravitize quantum theory instead of quantizing gravity. And by what he means by that is that he finds that the principles of general relativity are more fundamental, and that quantum mechanics needs to be modified in order to unify the two theories, because quantum mechanics already has problems like the measurement problem, and the fact that we don't know what is the wave function and so on. So that's why he really prefers to do that approach, and that means let's study how gravity affects quantum superpositions, for example. Quantizing gravity would mean let's keep the foundations of quantum mechanics as fundamental, the principles, and let's change general relativity to unify them. But I think you have to change both, and in order to bring them together. So I think Roger would also agree that that's quite likely. But yeah, I'm taking some steps towards that.
Is it related to Jonathan Oppenheim's work?
No, it's completely mine, an approach of myself, and it's also not Roger. It hasn't contributed to that new approach. I mean, it's inspired by Roger's ideas.
Okay.
And obviously it has, you'll see it. It'll have the flavor and the inspiration, but I don't even think Roger is aware of all. I mean, I did send him a draft, but I don't think he ever read it. And it has changed because, we started with some ideas. I'm doing that with my PhD students.
So again, just to you all, Ivette told me a bit about this idea off air, and it's so preliminary that I'm not even supposed to ask her these questions, but I'm going to ask you, what is the hurdle? So what is preventing it from getting more shaped or more sharpened?
Oh, yes, because we were about to publish, I think, was it a year ago? And actually, my husband called the model the equation that killed Christmas. Because I was not putting the turkey in the oven because I was calculating.
Oh, that's great.
Yeah, it was kind of a funny story. And then he teases me because he says, is it the equation that killed Christmas 2? So that was last year. And now I'm really trying not to do the equation that killed Christmas 3 and want to give it out. But yeah, no, I was about to publish last year, and then we were checking the cases and limits and stuff like this, and we found something that didn't make sense. And whoa, that was going back to everything from scratch. And I have a team of PhD students and a postdoc working with me, and so on. And well, I don't know. The funny thing is that we have come back to the same original model. So, but it's not like a circle, no? It's
Yes.
more like a spiral with a different understanding, because it's really kind of new. And I never had the experience of doing something new, because yes, new in a sense, but before I was working with quantum field theory in Curt spacetime, which is very established, and then quantum metrology, which is also very established, or quantum information, like, the theory of entanglement and things like that. And then I was kind of finding ways of bringing these things together to answer new questions. So in that sense, it was new, but I was using established theories. Whereas now we've gone out to, okay, let's make a new model from scratch. And it's been such a beautiful experience. My PhD students get excited and they say, we feel like we're doing real physics. And when you feel like you're doing new physics is when, or real physics, like they say, is when you have absolutely no guide, nothing to, in my previous work, I couldn't solve a problem, or I didn't know what to do. And then I would say, well, yes, but this is similar to the dynamical Casimir effect. Let me go and see what people working in the dynamical Casimir effect did. And then maybe that gives me some insight of what I'm doing here. So that was kind of the guide, and it makes things easier. But here, sometimes we've been in situations where we don't have that. So what's the guide? Are units. It's like, okay, this has to be a frequency, So when you're grabbing to the very bare, like the very basic of things, you feel like, okay, I'm out on a limb right now. And I don't know, I think we're getting there. And the thing that I'm kind of getting surprised is that on how simple things are turning out to be at the end. I don't know how I feel about that.
What do you mean?
Well, that we started out with a model that looked complicated, and we've been sort of working with it and trying to find out what are the different, let's say, instances of it, and it's kind of become simple at the end.
Does that please you or displease you?
I don't know. It confuses me. It does a little bit of both. It displeases me to some extent, because I think like, oh gosh, I should have seen this earlier. Because it's so simple now that I don't see how I missed things. It's like, this is too simple now. But I didn't see it before, and my students didn't see it before either. So it is what it is, But I feel like a little dissatisfied maybe by the simplicity, but I'm happy about it, because that means that taking next steps are not going to be so hard.
There's a quote from Wheeler that Wheeler said, behind it all is an idea so simple and so beautiful that when we find it, we'll look at ourselves and wonder how could it have been otherwise, and how could we have missed it?
Yeah. Yes. I don't know if we have such a, it is a model, and of course, it has to be tested, because, well, as a theoretician or mathematicians can come up with many models. And that's sort of the point, is that experiment is what tells us this is the right model or not. So that's also something that I like to talk when I teach to my students. So I teach quantum information in Southampton. And I like to say, well, mathematicians look at these mathematical structures, or they can come up with mathematical models and so on. But there's like an infinite possibility there. You like, algebras are so beautiful, and you can just get any algebra and you build a model out of that. And then I try to make the distinction between what a mathematician does and what a physicist does. And then the physicist would come up and say, okay, so this term is your energy, that term is the potential, this is an acceleration. That's why quantum mechanics is not a proper theory yet, right? Because we have a mathematical formalism that is super powerful, but we physicists have not been able to kind of connect the mathematical formalism, the wave function, to elements of reality, as we would do, for example, with, like classical physics, and you have some differential equations and you say, yes, but that's my mass, that's my acceleration, those are my forces. And then you have a proper theory. And well, this is how I see physics, right? And then you propose an experiment to test it, because mathematically, it's an infinite possibilities. Then comes this connection to physics. The physicist, for me, is the one who looks at the mathematics and connects the elements, like the mathematical formalism, with the elements of reality. And there you would already discard a lot of mathematical models, right? Because you might have once you think about what the equations mean, you might have some that don't conserve energy, and you might say, as a physicist, I don't like models that don't conserve energy, or this doesn't make physical sense for one reason. This doesn't really do what I would expect my physics to do. That reduces the number of models. And then, okay, you have this is like us, no? We have our baby that does what we think it should be doing, and we're very happy about what it does. Yeah, but maybe nature doesn't behave like that, no? And, as beautiful as the model might be, nature does what it does. That's why I think testing things in the experiment are so important. Now, the other thing is that, well, the experiment might say, no, this is ruled out, or you never really completely rule out things. It's very hard. But you could say, right, doesn't look good. But then you can see from the experiment what goes wrong. And then maybe that gives you like a good idea on how to modify your model to so it behaves better and according to nature. So I see these like 3 steps in being a physicist. Yeah.
Can you give me an example of where an experiment has gone wrong and then that led you to modify the experiment to something productive and new?
In my case. You mean in my particular, like in my work? Well, the thing is that there's only been 3 tests of things I have proposed so far.
Well, that's 3 more than most people.
No, not of people working in quantum optics. No, I mean, or in quantum technologies.
I see.
They do that all the time. Yeah, they do that all the time. So I haven't had the experience yet of saying like, okay, I propose this effect, or I get this theoretical result, and I write a few details more about how would you observe it in the lab, and put in some numbers to say how big the effect should be, and so on. And that the experiment comes and says, we don't see it. Okay, let me go back and change things. I haven't had that experience yet, because either things have not been tested yet, like the gravitational wave detector model that I proposed using a Bose-Einstein condensate. There hasn't been experiments to test it yet. But the other one that I mentioned, I was lucky that in the first go, I didn't have to change anything. There was like, yes, what you predicted was verified. So, yeah. I don't know. I maybe now we enter into that, but I hope we got it not too bad from the beginning.
So I have some questions about entanglement. Mm-hmm. Before we get to that, can you outline what entanglement is?
Yes. Entanglement is tricky to explain depending on the level. I was like recently doing that for like really young people, and I was like, oh my God, I have to think about this a little better.
So there are 2 classes of audiences that watch this. Mm-hmm. One are researchers, professors, postdocs, PhDs, and so forth.
Yeah.
And then another is lay people, artists, and gamers and what have you.
Yes.
So you can address it to both audiences. You can say, okay, the level one explanation is so and so, and the level 2 is this and that.
Okay, let me go first to physicists. I find it easier to explain, and then I'll see what I say in the other case, because this is improvised. No, I'm just haven't thought about it. So in quantum mechanics, you say that the state of a system, let's say one system, so let's think about a spin half particle, can be in a superposition of up and down. No, so this is the wave function. This is, again, we're not going to interpretations of is a particle really up and down at the same time. Let's just keep it as the state of the system is given by a vector in the Hilbert space. So I would say that is like the first postulate of quantum mechanics. But then you want in quantum mechanics to describe what happens if you're now describing two particles or two systems, not just one. So we say that it's a bipartite system. So the way that you do that in quantum mechanics is a special mathematical way called the tensor product. So you take the Hilbert space for this system where your state is the vector in the Hilbert space, and now you add a second system. So the total Hilbert space is the tensor product space of the two. And then in this bigger Hilbert space, you also have a bunch of possible states. And if you look at the states, there are some special states in which you cannot write the state in what we call a separable state. So a separable state would be this particle is in, let's say, some superposition, tensor product, this one. So these states, physically, let's say, you can produce by local operations and classical communications.
I love this.
Yes. So let's think about Alice and Bob preparing quantum states, so of a bipartite system. So let's stick to the spin example and so on. So let's say that Alice is in her lab and Bob is in his lab. So then local operations means that Alice and Bob separately in their lab are allowed to do whatever they want to their state. So they can rotate it, they can do a quantum gate on it, they can even measure it. And then classical communication means, they use a photon to send information. They talk on the phone. Alice says, I'm going to measure in the Z direction, and any kind of things that they want to agree on the phone, that's classical communication. So if they take their spin particles, each one has their spin particle, and they only do local operations and classical communications, the states will always be separable. Now, there's another type of states that are like the entangled states, and those cannot be produced by only local operations and classical communication. They need some interaction. So the interaction could be bring the two spin particles together and then do like a spin-spin interaction. And then you produce like a global state. And we talk more about what entanglement is in a moment. But before, you could also entangle them by having Alice get her state entangled with, say, a photon. So a third system, but a photon is a good example. Then you send the photon to Bob's lab, and the photon interacts with his spin particle or his system, and then these two become entangled. But they require some interaction. So this means a global, not a local operation, and so on. So what's special about entangled states is that they're very highly correlated. So more than any classical correlations that you could create. So the classical correlations would be Alice and Bob talking and say, okay, look, if my state is up, yours is up too. And my state is pointing down, yours is too. And they could agree on any number of combinations of that. And that is all classical correlations. But what happens with entanglement is, well, on one hand, if you make a measurement in Alice part of entangled pair, the state of Bob will be sort of immediately take a certain state. No?
Mm-hmm.
So the states of Alice, so in Alice's points of view, her state is in a superposition of up and down. So she doesn't really know what state her system is. It's not just that she doesn't know. It's indeterminate until she measured, because it's in a superposition until she measures. And Bob's state, the same thing. But if they're not entangled, if they do this experiment many times, the outcomes will be not correlated. But if they're entangled, let's say if it's maximal entangled, like a Bell state, they will be completely correlated. So every time that Alice makes a measurement, then that will determine Alice's state, and that immediately gives Bob like a given outcome. So in that sense, what Alice does in her lab affects the outcome of the states in Bob's lab. And that's very different to what happens classically. That never happens classically.
Just a moment. Before we get to the explanation for the lay people, the people who aren't physicists or aren't mathematicians, it's said that the correlations are in quantum entanglement are stronger than can be classically. Okay. But then in the example that you gave where I usually say Angelina and Brad instead of Alice and Bob.
Yes.
So Angelina, she says, look, I have a spin down, and Brad says, I have a spin down as well. And then it's usually the opposites in the real world, but doesn't matter. Can't you just have a coin? A coin is, if you see that it's heads, the opposite is tails, that's a 100% correlation. And so how can you ever beat a 100% correlation? What does that mean? Give an intuition to that.
Yeah, okay. Okay, so the intuition, I think I would say, is like, if you think again about a spin half particle, you could measure the state in different bases. So let's think about this example. We was talking of spin particle in a magnetic field. So the state could be pointing up or pointing down, or in a superposition of up and down. But if I measure in that direction, in the set direction, what will happen is that I will find either the state up or the state down. But in quantum mechanics, you can choose a different angle. So let's go to the set plane. So let's say if the state was here pointing up, when you measure in that direction, it's also going to be 50-50, either, like pointing this way or pointing the other way around. So take another angle, like at 45. So if you take there, it's also going to have a probability of being pointing in that direction or in the opposite direction in that angle, right? So when you have an entangled state, you will always find perfect correlations. Okay, so the coins are perfectly correlated in one instance, right? In the heads or tails. And that's it. That's the only thing you have. But in this quantum example that we're talking about, you can make measurements in how many bases?
I see.
An infinite number, because you have in the sphere, you have an infinite number of possible angles, right? So so that means that you could choose among an infinite number of possible bases, and the state would always be correlated.
So the amount of questions you can ask the coin is just, are you heads or are you tails? Whereas the amount of questions you can ask the quantum system is infinite.
Yeah. So if you would say, but Alice and Bob cheated and they agreed on, they shared this information, well, they would have to, in principle, share an infinite amount of information in order for you to see that sort of outcome.
Great.
Yeah.
Okay, now explain entanglement.
Okay, I explain
the ELI5 version.
No, I don't know. I mean, I think the intermediate one is like really hard.
How about the 15-year-old then?
Yeah, I tried to explain it to children. It's like really, or
forget about children. Children are watching
13-year-old. I meant it's hard, But what I used was Bertelsmann socks. Do you know about Bertelsmann socks?
Bertelsmann socks.
Yes.
No, so I know about socks.
John Bell.
Yes.
Had a student who still lives in Vienna, Reinhold Bertelsmann. He's a wonderful professor. But John used his student, his PhD student at the time, as an example to teach people what our classical correlations are, because every time you look at his feet, that he wears one green sock on one foot and then a red one on the other. So like he would use this example to measure, to see, what correlations are. And actually, what's really nice about Reinhold, that he's still in Vienna, is that if you find him in the supermarket, you will still see that he always wears one green sock in one foot and the red one in the other one. So I think that is like a good way to explain what classical correlations are. And then I was kind of trying, I had very little time, and I had to and then I was trying to explain how would like the quantum version of the socks work. And it's a bit like you're wearing these socks that are undetermined, right? They're red and green at the same time. But now you need like two people playing socks, so somebody has red and the other ones have green. This is kind of the child explanation, but for audience that are adults, I mean, it's like a little bit like too simple, maybe. It doesn't really make much sense to explain it with socks, I think. But I think that the lesson is that the correlations are stronger than the classical correlations. So I think the coin example is very good. You would say, well, you can create classical correlations by producing some sort of outcome in which you always get the same outcome, and you. Like in the example of the socks, you could agree on something so that when you make the measurement, you find the same result. But quantum correlations are much stronger than that. I think the spin half example that I did, I think this is probably not too bad for the other audience, no? Or you think it is a bit...
No, it's perfect.
No?
Okay, theoretically speaking now, what do we know about entanglement in a relativistic setting? And then we can get to the experimental side after.
Yeah, so that's how I started thinking about, let's say, quantum mechanics and its connection with relativity. Because when I learned about entanglement as a undergraduate student, my teacher said, okay, you have these spin half particles, you bring them in contact, you entangle them. Alice takes her qubit and Bob takes his part of the state, and then they use them to do teleportation. But nothing mathematically, theoretically happened to the state. There was a Bell state, and I was just told, okay, now Alice and Bob separate. And for me, that made no sense. I was thinking like, well, but what happens if they're doing that in the presence of a gravitational field, if the space-time is curved, if they're moving close to the speed of light? What happens? The entanglement is always the same. That doesn't change. And I became interested in that question.
Quick question about your question. Why would you expect it to change?
Well, I mean, because you have in relativity that often things depend on the state of motion of the observer, right? So clocks change, the ticking of the clock depends on the state of motion of the person carrying the clock, or you also lengths and so on. So for me, it was kind of quite obvious that, we needed to either show theoretically that is conserved under all circumstances, or it's not. So I was curious, and I wanted to know how could I study that. But then, I mean, I kind of forgot that I was worried about for some time, and I just learned about entanglement and so on. But then I became a postdoc at the Perimeter Institute. I think I told you that story before. And then what happened is that my friends were working on gravity, and I became sort of very jealous of that. And I thought, oh, I want to learn more. And I thought, well, I've already changed fields a few times. So I thought maybe it's not a good idea that I change fields yet another time. I had some nice papers already in quantum information. And I started to sort of merge things. So I started to think about what happens. How can I think about entanglement in relativistic settings? And that's how I started to learn, because I didn't know it before, quantum field theory in curved space-time. And the first paper that I wrote on that direction is called Alice Falls into a Black Hole. So it's like entanglement in non-relativistic, in non-inertial frames, because some colleagues had looked at what happens to entanglement, sort of if you change the state, but everything inertial from the perspective of different inertial observers. And then I thought it would be interesting to find out what happened with the description of entanglement from the perspective of different non-inertial observers. And that I found like a result that for me at the time was surprising, because I thought that entanglement was like a property of the system. No, so you have these spin particles like we were just discussing, and they are entangled to some degree, maximally entangled if you want. But in quantum mechanics, it's like clocks always tick at the same rate. The underpinning transformations are Galilean transformations. So entanglement is sort of a conserve, or we don't even think about what happens from entanglement in a different perspective, because that's more like a question from relativity. So I was interested in finding out then what would happen. And what I found out is that the degree of entanglement in the system dependent on the description of the different observers. So later on with Paul Alsing, I wrote a review called like Entanglement, Observer-Dependent Entanglement. And at the time, it was for me surprising, the connection. But that is how I started to work in the interplay of quantum mechanics and relativity, asking questions about entanglement. And for example, another thing we did, and that was with Frederick Schiller. We looked at if you have a state that is separable, let's say in the past infinity, and then you have a period of expansion. We did toy models, really, like the Robertson-Walker universe and so on. What happens to like the state in the future? And we found that, the expansion of the universe would produce entanglement between particles created by the expansion. But these were all very toy model questions. I mean, the universe doesn't even behave like a Robertson-Walker universe. We know that. But we were learning how to think about entanglement in sort of relativistic settings. And you had to be careful with things like particle create, like different in curved space, like different observers don't agree on the particle content of the field. So how do you think about entanglement in that case? In quantum information, what you need to talk about entanglement is to make a bipartition. So maybe you have many particles, like spin particles, but you say, okay, the left side is system 1 and the right side is system 2. And I look at entanglement between these spins and that spins. But you can also make a different bipartition and say, like, all the spins looking up versus all the spins looking down. How entangled are they? And then that's a different bipartition. But you need to give me the bipartition and then you calculate the entanglement. But in curved space, different inertial observers completely disagree. So this notion of subsystem was like, I started to learn how difficult it was becoming to describe. So that was one of the first kind of problems that we found with studying entanglement in relativistic settings.
Ivette, thank you so much for speaking with me for so long. I want to get to advice you give to your students. Do you have any consistent advice?
Oh, yeah. I think I give them advice all the time. I don't know how much they like that. But you mean, one of the, I guess, like the advices that I give them sometimes is that to follow their own sort of direction, in spite of sometimes can be like the community can say things that are like, well, you need to, everybody does this or everybody does that, and that sometimes you have like a unique way of looking at things. And I try to encourage them to do that, but always with, the rigor that you can have with the mathematics. There's several ways that you can be rigorous with your science, and one is with the mathematics and being, sure that everything is sort of consistent and so on. And the other is and ideally with both, with the experiments. So I try to encourage them to be creative, to be courageous, to follow their new ideas and so on, but to keep, let's say, safe by taking any new step as rigorous as possible.
Thank you.
Thank you.
Hi there, Curt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at curtjaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's CurtJaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted. There's zero spam. This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Curt, you've spoken to so many people in the fields of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. CurtJaimungal.org, or search Curt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/toe, TOE, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. Toe is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/toe, TOE. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that Toe listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use, I'm there with you. Thank you for listening.